So with this, we are finishing the discussion. So we talked about point defects. We talked about one-dimensional line dislocations that are also defects in crystalline materials. So the next extension for us would be to talk about two-dimensional features in the materials. So we will talk about two-dimensional defects. We already mentioned some of them, like grain boundaries. But as the first topic in terms of the surface features and the surface properties of the materials, we will talk about the surface energy. Okay? So when you have a piece of a material, right, and if this is a crystalline material, the atoms will be bonded and they will have a certain number of nearest neighbors. And again, the number of the nearest neighbors, the density of the dangling bonds, the density of the atoms, etc., depends on the symmetry of the crystal and other details, the bonding type, etc. But you can predict that if you know the material, you can calculate this, and you know the symmetry of the crystal. So now imagine that you have a piece of a material. It's a three-dimensional crystal, and you want to break it into two. Right? So the question is, what is the surface energy, and why do we even care about the surface energy that is created by this? So if this was the bulk of the material, so everything beneath this point will be again in the crystalline material, and this will be your surface. So this is newly formed surface. What physically happens during this breaking process is that the atoms that otherwise in the bulk would be above these atoms on the surface are simply disappear, right? So they're in the other part of the material that is broken off. So what that means is that there is a certain number or a certain density of so-called dangling bonds. So these are the bonds that correspond to the surface atoms that are not connected to anything. So we will talk in the next couple of lectures also about the fact that these dangling bonds can reconstruct. But to calculate what is the probability or what is the energy per surface, we will define something that is called excess surface energy per unit area. In other words, to form a surface with certain number of the dangling bonds in a given crystal, this surface energy for this particular plane will be very different than if you want to break this particular crystal in another direction. And the reason for that is that you're destroying or you're forming a certain number of the dangling bonds that simply depend on how you cut this material, how many dangling bonds per atom do you break, and what is the areal density of the atoms. Okay? So we will talk about this in the remainder of the lecture. But the excess surface energy per unit area then will be typically expressed in terms of the joules per meter squared. And the surface energy really plays a significant role in many, many processes or many features within the crystalline materials. So one of them is the shape of a crystal. So the shape of a crystal or the shape of a material in general is determined by the surface free energy. So in principle, this free energy has to be minimized for a given crystal. So you either want to minimize the overall area of the crystal, or you want to form the crystal where the surface energy is minimized by forming the facets that have the lowest surface energy, right? So, for example, when you think about a droplet of water, the reason why it's spherical is because that minimizes the surface of the material per given volume, right? So, therefore, the surface energy will be minimized. If you have a crystal, so this is a set of crystals that were grown at the same time, they have the same composition, and you see that they all have relatively similar shapes. If you grew different crystal under relatively similar conditions, the shape of the crystal might be completely different. And the reason why these particular crystals have these equilibrium shapes, that we will also call wolf shapes. Again, these are the facets that have the lowest energy for a given crystal. So in principle, if you know what is the symmetry of a crystal, if you know how the local bonding looks like within the crystal, you can predict what will be the equilibrium shape of that crystal. And this is called Wolf construction. So you can predict, you can calculate the surface energies. There are different methods. We will go through a very simplified version of that calculation. And then you can use the Wolff construction to predict the disequilibrium shape. So just to give you an example of the Wolff shape construction, we will go through an example of an FCC crystal. So we basically have to understand, if you have a certain surface within the crystal, how many dangling bonds are broken and how many atoms are in that particular surface area. So if you consider an FCC crystal, so this is a face-centered cubic crystal. So there are atoms in the corners, and each facet has the centralized atom. So, and if you, for example, consider 001 surface. So 001 surface will be this surface here. So to calculate the number of the dangling bonds, we have to understand what are the nearest neighbors of each individual atom and how many of them disappear when you remove a certain portion of the crystal above this certain plane, which in this particular case is 001. So the first step is to understand what is the coordination number. So what is the coordination number, or what is the number of the nearest neighbors in an FCC crystal? Yes? Can you? 12. Okay. So if you take a given atom here, so the coordination number for an FCC crystal is 12. So what that means is that, for example, if I take this particular atom in the center of the 001 facet, there will be this atom here, this atom here, this atom here, and this atom here that are below the 001 facet. The distance between them is a square root of 2 over 2. So then there is another set of atoms that are the ones in the corner. They have the same distance. So this is 8 atoms in total. And where are the rest of the 4 atoms? They're pointing up, right? So they're at the facets of the unit cell that is above the one that we plot here. So they're here. So this would be the central atom on the facet in the unit cell above. And there is one that is facing out of the plane. So if I ask you a question, if you break a crystal along the 001 surface, how many of the broken bonds, or how many bonds will be broken for this particular atom? So to know that, you have to calculate, or you have to understand how many of the atoms that are nearest neighbors to this atom remain in bulk, and how many of them are removed by cleaving this facet along this particular direction. So how many of them are removed? 4. Okay, so what are the 4 atoms that are removed? The ones above, right? So if I shade them, so this would be this one, this one, this one, and this one. So it's 1, 2, 3, and 4 atoms. So there are delta bonds, or the change of the bonds, or the number of the bonds that are broken per atom, bless you, is equal 4. I also have to calculate how many atoms there are per surface area in this particular plane. So the surface is equal to a squared, where the A is the lattice constant within the crystal. How many atoms are in 001 plane? What is the areal density of atoms? 2. Okay, so why do we have 2? Is equal, so we have we have 1 atom in the center that contributes to this particular area, plus 4 atoms in the corner, each contributing to 1/4, which is total of 2 atoms. So what that means is that we have 2 atoms per the surface area of A squared, and each atom has 4 broken bonds. So in principle, I can calculate the surface energy for this particular plane, 0, 0, 1 plane. Okay, let me just try to write it here. So this will be 2 atoms per, and there are 4 broken bonds, times the energy of the bond divided by the area. This will be equal to A over 8 over A squared times the energy of the bond. Okay? So we can do the same exercise for any given plane within this particular crystal. We do the same analysis, right? So we will go through one more step just to illustrate the different planes in a given crystal have indeed different surface energy. And we will calculate this surface energy for 110 plane. So 110 plane will be this plane here. Okay, and again, each particular atom will have 12 nearest neighbors. And the ones that are disappearing, so if I assume that I'm cleaving this crystal in a way that everything above the plane remains in the bulk and everything below is removed, then I have to calculate what is the number of the nearest neighbors that is being removed through this process. So when I calculate this, then there is 1 atom here, then there is another atom here, so this is 2. Then there is the atom that is on the facet of the unit cell that is going out of the paper, this is 3. There is the atom in the corner here, and the 5th atom will be at the bottom of a unit cell here. So in this particular case, there are 4 bonds that are being broken per atom if you cleave the material along 110 plane. So we have to go through the same exercise. We have to calculate, so we know that this number of the bonds is now 5. We have to calculate the surface and the number of the atoms. Okay, so the delta bond per atom is equal to 5. Surface is equal to A square root of 2. And the number of the atoms, what is the number of the atoms in 110 plane? This comes back to something that we covered at the beginning of semester, right? So how many atoms do we have in 110 plane? 2 of them, right? So there are 2 atoms that contribute with 1/2. So these are these atoms. And there are 4 corner atoms, each contributing with 1/4. And I can do the same calculation as before. So gamma, and I apologize for this, I can't really write below, but gamma for 110 then can be calculated as 2 atoms, 5 broken bonds times the energy of the bond divided by the A squared square root of 2. And this is equal to 5 square root of 2 over A squared times energy of a bond. Okay? So with this very simple exercise, we just calculated what would be the surface energy for an FCC crystal along 001 and 110 plane. In reality, there are many more calculations that one has to take into account, specifically the second nearest neighbors and details like that. But in general, this is the way how things are calculated.